Question 6. What is the major problem associated with the re-entry of a spaceship through the Earth's atmosphere? Is it the G-forces and the heat due to the atmospheric friction? Is it the angle of re-entry? Is it the increase in speed due to gravitational forces? Or is it the use of ceramic tiles to minimize heat transfer? I hope you've realized by now that the answer is A. The G-forces and the heat produced by atmospheric friction are the greatest dangers to any astronauts attempting to re-enter. Question 7. During part of a typical re-entry, the spaceship is unable to communicate with ground stations. Why is this? Is it because the spaceship is moving too fast to communicate? Is it a buildup of a dense cushion of air under the spacecraft, sort of blocking the signal? Is it heat due to atmospheric friction affecting the electronic communication equipment on the outside of the spaceship? Or is it atmospheric friction ionizing the air underneath the spacecraft? So the answer, of course, is D. This is called an ionization blackout. Ionized air is air that has been split into charged atoms and electrons, which is a very good conductor of electricity called plasma, and this will block any radio communications. Question 8. Explain the concept of sacrificial layers on re-entry spaceships. So, what could a sacrificial layer possibly mean? I haven't used the term so far, but I'm sure that you would be able to guess what it means. It is, of course, an ablative heat shield. Older re-entry vehicles used an ablative heat shield, consisting of metal alloys, fiberglass, and ceramics, in order to protect the spacecraft, right? As the vehicle descended through the atmosphere and got hotter and hotter and hotter, the heat shield will eventually heat up, begin to melt, and begin to ablate, and begin to vaporize. And because this takes so much energy to do, none of the rest of this energy reaches the rest of the spacecraft. So in effect, you're sacrificing the heat shield in order to save the rest of the ship. And this is why it's sometimes called a sacrificial heat shield. Question 9. What would happen to a spacecraft if it tried to re-enter the atmosphere at a very shallow angle? So in this case, we wouldn't be able to re-enter properly. What would happen is that instead of managing to go down and into an elliptical orbit around the Earth that takes us deeper into the atmosphere, we'll instead move higher up again. We'll bounce off the atmosphere. We'll have too much lift for a successful re-entry. All right, what about the opposite? What happens if we enter at a very steep angle? In this case, we will in fact move back toward the Earth, but it will be too fast for us to actually survive it. If we move steeper toward the Earth, then we'll get a lot of air resistance far more quickly. This produces more heat, and it produces more G-force. So if the re-entry angle is too steep, we'll encounter so much air resistance that the entire craft will in fact vaporize. I mean, even if it didn't, the G-forces will be strong enough to break apart anyone on board. Question 10. Giving reasons for your answer, in which direction should astronauts be facing during takeoff? So remember, if we want to minimize the harmful effects of G-forces, we need to use an eyeballs-in approach. That is, have the G-force acting in this direction, right? Now, if we're launching upwards and we're accelerating upward, that means that the G-force will be acting downward. So, if we want to minimize the harmful effects, we ought to be facing upward in the same direction as the acceleration, right? So we should be lying down and facing upward during takeoff, so they are pressed backwards into the contoured couch as they accelerate upwards. Now here's an interesting question. Which way should they be facing during re-entry? I'll let you think about it for a moment. In this case, once again, we need to consider the g-forces involved. Now, normally g-forces point toward the ground, but given that we're coming from a weightless environment, space, would that be different somehow? Of course, it all depends on the acceleration of the spacecraft. If we're accelerating downwards, that means that we need to be sitting at sort of the top of the spacecraft looking down. If we're accelerating upwards, then we need to be at the bottom of the spacecraft looking up, right? So which case is this? Re-entry. Are we accelerating up or down? Well, we're descending, but we're slowing down, right? So if we're moving down but at a slower and slower rate, that means we have negative acceleration. So we have acceleration in an upwards direction. That means that, once again, we should be at the bottom of the spacecraft facing upwards, facing, in fact, in the same direction as when we launch. This means that the g-forces will press down on the astronauts and push them into their contoured couches, and that will, of course, minimize the harmful effects of g-force.